Welcome to the world of Rust, where fearless concurrency meets the elegance of borrow checking. In this captivating video, we'll dive deep into one of Rust's most powerful and distinctive features, borrowing. Brace yourself for an adventure that will shine a light on the mysteries of borrowing, showcase its ingenious design, and demonstrate why it's a game changer for writing safe and efficient code. Whether you're a seasoned Rustacean or just beginning your journey with this innovative language, understanding borrowing is essential to harnessing Rust's full potential. Get ready to sharpen your programming prowess as we explore the inner workings of the borrow checker. My name is Max, and I will equip you with the knowledge and confidence to write code that not only compiles without errors, but also runs with blazing fast performance. So, fasten your seatbelts and join me as we embark on an enlightening quest into the heart of borrowing in Rust. Well, that introduction might have been a tiny bit over the top, but I'm really excited to show you how borrowing works in Rust because it's one of its coolest features ever. So, last time we had ownership, and ownership told us you can only have one owner for some data, and once this owner goes out of scope, the data is dropped and the memory is freed. This time we're going to talk about how can we share data between multiple functions and multiple variables. So for this, let's start very basic. Let's say we have a variable called message, and this message is a string, and it just says hello there. Now for whatever reason, I want to have two other variables that also have read access to this message. So we'll call it message2, and this one is going to borrow from message1, so we'll have an ampersand as a reference operator and put message in here. And that's already all the magic for immutable borrowing. Now message2 can have read access to everything that is in message. And because that is so cool, we're going to do it another time, just to show you that this will work for three variables as well. So we have message3 here, also borrowing read access to message. And now we can use all of those at the same time. We can say message1 is equal to, and we'll input message here, then we have message2 is equal to, we put message2 in here, and the same for message3. And you can see Rust compiles this without error, and we get no surprise here. 3 times access to the same data structure that always contains hello there. So we can put down our first rule about borrowing, which will be you can borrow as many times as you like immutably from the same variable. So any number of immutable borrows can happen at the same time. Now, of course, this was a very trivial example and you would never do that in reality, but I just wanted to set up a very simple example to show you how borrowing works. Basically, all you need to remember is use this ampersand operator and you will get access to whatever is in the original variable. Of course, occasionally you will also need mutable access to another variable. So let us, for example, take this variable numbers, in which we want to store a string that contains all the whole numbers, starting from 1. Now we want another variable that has mutable access to this, so we'll call it numbers borrowed, for lack of a better name. And we'll have the ampersand to indicate that this is a reference, so we're borrowing. And we have the mute keyword to tell us this is a mutable reference, so we want to have write access to this other variable. And the other variable is of course going to be numbers. So now it would be easy to think that we can just write to the string from both sources, so from numbers and numbers borrowed. But let's just try what happens if we do that. So for example, if we say numbers.pushString, and for now we're going to add number 2. And then let's use numbers borrowed, push string, and we're going to use the 3 to append here, suddenly Rust will not compile this anymore and we'll get an error. Why is that? It says cannot borrow numbers as mutable more than once at a time. And it tells us that the first mutable borrow occurs here. So we have the borrowing operator here. And the second mutable borrow occurs here because now numbers itself, the original variable, tries to write to the string. And for all intents and purposes, you can view the original number also as a reference to this data structure, to the string. So therefore we have 1, 2 references that both want to mutate this variable, so they're mutable references, and Rust will not allow for that. The reason for that is that in this way Rust can guarantee that no data races will occur. A data race would occur when you have multiple variables that have access to the same data structure and you're trying to mutate this data structure from at least one source. And therefore, the other sources are never quite sure in what state the actual data structure currently is. However, Rust is quite clever about this. So if we put this access via the original numbers variable up here, before we borrow with the numbers borrowed, then everything will compile just fine. This is because Rust knows that the numbers variable, so the access via our numbers variable to the string, will lastly finish here at line 10, and only after that we have the mutable borrow via numbers borrowed, which can then be the only access to this data structure as from here. So not only when a reference goes out of scope it will be inactive, but Rust will also check for the last use in your source code, and from then on it will assume that this reference is inactive, and you can therefore create a second mutable reference, which will then take over to be the only one. So let us play around with this concept a bit more. Let's again say we have a variable, in this case I'm going to call it the alphabet, and this is just a string that starts with the first lowercase character of the alphabet, which is A. And in this string we're going to try to build up the alphabet by just pushing back the next characters. And this time I want to have an observer variable. So I don't want read access, but I just want write access. So we create the observer here. And this is just a reference to our alphabet. Now we're going to change the alphabet. As we already said, we're going to push the string comma B. And because the observer's job is to observe, it will occasionally just print what the current state of the alphabet string is. And again, we get an error here and Rust will not compile it like this. This is the safety that you get from Rust. So you create an observer at this point here, line 15, and this is a reference to the original data structure. And Rust guarantees you that as long as the immutable borrow, so your reference to the alphabet, is being used, it is going to be in the same state all of the time. And because alphabet push string here in line 16 would change the state, it is not allowed. So we can derive rule number 2 from this. If a mutable borrow is currently active, no other borrows can happen. So we saw that we cannot have two mutable borrows at the same time, and we can also not have a mutable borrow alongside an immutable borrow. So let's just get rid of this line to get our code to compile again. In order to explain to you the third safety that Rust will provide us via the so-called borrow checker, which is the part of the compiler that always gives you those errors when something with borrowing is wrong, we will take a look at a reference that is no longer valid, or we will at least try to create one. So we have an outer scope variable. We call it an outer scope ref, and this is going to be a reference to a string that we are not going to initialize right now. Then we'll create an inner scope, and we'll have a string in there, the inner scope string. And we'll just call it inner scope. Now we're going to try to assign the outer scope reference to the inner scope, which means we're borrowing immutably. So outer scope ref is equal to ampersand inner scope string. And then we're going to try to use this reference outside of the scope. So what would happen here if Rust were to compile this, which it doesn't, is that the inner scope string is only valid inside the scope. So as long as the scope lives, the string has this data inner scope. But as soon as we go out of the scope, the string is going to be dropped, meaning the memory that has been allocated on the heap will then be freed and is free to be used by any other software on your computer. So you have no idea what kind of data will be in there. However, here we try to reference this data that will then be dropped from outside of the scope. And Rust will tell us, and rightfully so, that the borrowed value does not live long enough, meaning the inner string dies or is dropped at this point. However, we're trying to use it outside of the scope, which means after its lifetime. So we get the third rule of the borrow checker, which is references must always be valid. And those are the three simple truths that you can always remember about the borrow checker. You are allowed to make immutable borrows at any number at the same time. However, once you have one mutable borrow, no other active borrows can happen at the same time, and you are never allowed to create an invalid reference. And Rust will always check for those things, even in very complex scenarios, via the borrow checker, so that once you break one of those rules, your program won't even compile. And this is to ensure that there is no data races, you don't have any dangling references, meaning that a whole host of problems that are very prominent in C, C++ programs are not even possible to happen when you program Rust. And this is the beauty of borrowing and the borrow checker. Let us get rid of this code for now and take a look at more realistic scenarios where you would use borrowing, which is when you need to transfer data from one place to another. So the one way we know until now to do this are functions. So let's create just one function where we transfer ownership. So we create a function, call it transfer ownership. And for this, we're going to have an input, which is going to be a string. And we're just going to print this for lack of better use. Transferred ownership of, and then we're going to use this string here. Of course, in order to make sense, we need to use this function. So in the main scope, we will just create a variable s1, which is a string containing exactly s1, and we will transfer ownership from s1. Straightforward. Now, if we run this code, everything will be working just fine. We see the print line transferred ownership of s1. And if we were to use this string s1 after we've already transferred ownership, trying to use, we'll put s1 in here, in the main scope, after transferring ownership, and we'll put s1 in here. Of course, we get an error by the borrow checker because it said that this parameter takes ownership of the value, which is our function input here, and therefore we're trying to use a value after it has been moved, which is invalid syntax. So this line will never compile because the ownership has already been transferred into this function, and actually this function just drops the input variable, which means it's deallocated from memory. Additionally, if we would like to mutate this variable, we can put the mutable keyword in here, and we can then do something like input.pushString, and we just append the mute. Of course, this will not have any influence on S1 in the main scope, only within this transfer ownership scope, but we can see that if we wanted to mutate this variable, that is totally possible. So number 2, let us now check out how we can use borrow immutably from a function. For this, we will create a function which is called immutable borrow. And we'll take again an input string, but this time we will put the ampersand in front of the string to indicate that this is a reference to a string and therefore it is borrowed immutably. And all that we can do is now read from this variable, therefore we will just write immutably borrowed and we will print the string. Again, let's call this function from the main scope. Of course, we need to use a new variable here because S1 has transferred ownership already. So we'll create S2 and we'll call the function here immutable borrow of S2. And in order to show the compiler that we want to borrow this variable to the function, we will again use the ampersand and put the S2 here. Now for the time that this function is currently running, it will have a mutable reference to our string S2 from the main scope, and after it's done running, this mutable reference will be destroyed. However, the main data structure still is owned by the main scope, which is here in S2, so we can definitely use that afterwards here, returning from immutable borrow, and you will see that S2 is unchanged, still contains the string S2. A third option, of course, is making the mutable borrow. So we'll just copy this function and change it a bit. In order to have a mutable borrow, you have the ampersand with the mute keyword afterwards, then a space, and then the type of the variable that you want to mutably borrow. Then let's just change the text here to make more sense. And of course, because we mutably borrow this variable, we can just change it as we want. So I'll just do push string and we'll append the mute keyword. Now let us call this function from the main scope. We will create a new variable S3 containing the S3 text. Then we will have the mutable borrow of S3. Now in order to indicate again that we want to mutably borrow to this function, we need the ampersand for a reference and the mute keyword. So we tell the compiler this is a mutable borrow and we put in S3. And of course, for this to be valid, we will have to have a mutable variable S3, otherwise we cannot mutably borrow. And now when we get back into the main function, we can say we're returning from mutable borrow and we have S3 here. Now let's run this. We see that within the function we first change the variable by adding the underscore mute. Then we will return from the mutable borrow to the main function and we see that in fact the data is changed. It now has S3 underscore mute as its data. As you can see, all the rules of borrowing within one scope also apply to borrowing via functions. So if you have function parameters, you can transfer ownership, you can have an immutable borrow, you can have a mutable borrow. And the nice thing with Rust syntax is that even at the point where you call this function, you will right away see what will happen to your variables. So here you can see if you just transfer S1 like this, that ownership will also be transferred. If you use the ampersand, then you will be calling a function that has a immutable borrow. And if you have this ampersand and the mute keyword, this is a function that mutably borrows your variable. So you need to expect that whatever content is in there will be changed. And there you have it, fellow adventurers. We've journeyed through the intricate world of borrowing in Rust, unlocking its secrets and witnessing its extraordinary capabilities. Congratulations on reaching this milestone in your Rust learning. By now, you understood that borrowing is not just a mere technicality in the language. It is the cornerstone of Rust's safety guarantees. Embracing borrowing empowers you to write robust, bug-free code that is performant and maintainable. As you continue honing your Rust skills, remember to practice, experiment, and don't shy away from encountering borrowing-related challenges. With time and experience, you'll master this essential aspect of Rust programming, and it will become second nature to you. Keep exploring the vast Rust ecosystem, contributing to open source projects, and engaging with the vibrant community. Remember that learning never stops, and the knowledge you gain here is just the beginning of your exciting Rust journey. Thank you for joining us in this adventure. If you found this video helpful, don't forget to like and share it with fellow developers who are also eager to harness the true power of Rust. Subscribe to my channel for more engaging content on Rust and other programming wonders. Until we meet again on the next thrilling quest, happy coding, and may your Rust adventures be filled with joy, triumphs, and of course, stay comfy.